So, we continue to discuss the impact analysis. So, this was the example what we discussed in the last lecture. We are talking about simplified impact analysis. So, if you look at for kinematics in this case, S should be equal to Rs and Rp. For force equilibrium, P, the impact load, should be K into S, will also be equal to K ship into Rs, will also be equal to K platform into Rp. Suppose if I know that the Ks and Kp are the idealized stiffness of the ship and the platform respectively, I can find Ke, which is equivalent stiffness, to model this problem as 1 by Ke is 1 by Ks plus 1 by Kp, looking at this figure, equation number 3. So, since this is the motion or displacement of the ship, acceleration of the ship can be d square s by dt square. The interacting force P is minus ma. I can now write the equation of dynamic equilibrium of this, where m is nothing but the mass of the ship plus added. So, the differential equation for impact is given by set to 0. For the given initial conditions, the solution of the equation 4 is harmonic. Which is given by S is equal to V naught m by Ke sin omega t. Call this equation number 5. the natural frequency omega is square root of Ke by, yeah, where K is the equivalent spring stiffness, where K is the equivalent spring stiffness, which is 1 by Ke is that of the ship and the platform, like this. This will be in so many radians per second. Okay. So, let us find out the maximum value of the interacting force. Which I call as F max, which is S into S max into K. S already we have here, so I can simply say V naught root of m by Ke going to be F max. Call this as equation number 7. This is 6. I am looking for the maximum force. Now, the time for the first contact, which we are interested in, which I call as T naught, to the maximum force or to cause the maximum force, this is small t naught, is given by T naught pi by 2 of root of m by K. This may duration of impact or collision. F max can also be computed by the other way. By an alternate method, you can compute F max. This is on the basis of law of conservation of energy. We already know the deformation energy of the ship which is given by Es which is half Ks Rs square, equation 9, and that of the platform EP is half Kp Rp square. So, equation 9 can also be written as ES is F max square by 2 Ks. Similarly, equation 10 can be rewritten as EP is F max square by 2 Kp. Combining equation 11, we get, let us say F max square by Ks plus F max square by Kp should be equal to my total kinetic energy of the vessel before impact, which is Ek, is it not, considering there are no fenders. No fendering action, this is F, no fendering action. Oh. So, that implies F max square by 2 1 by Ks plus 1 by Kp is half m V naught square, that is my kinetic energy. You can also find out F max from this equation. Alternatively, using the conservation of energy, I call this equation number 12b, this is 12a. Now, ultimately I am interested in estimating the impact duration. The impact duration T naught is given by pi by 2 root of m by Ke. Let us take up an example and see whether this example demands a dynamic analysis or a quasi static analysis for the impact. We will take up an example and see. Let us say I have a vessel is drifting with a velocity of 2 meter per second. The displacement of the vessel is 2500 tons. The hydrodynamic mass that is the added mass is about 40% of its own mass. This is for the ship, not for the platform. This is also for the ship, it is a vessel. Okay. So, now we have a data as follows: m is 2500 plus 40% of 2500, which makes 3500 tons, okay, and V naught is 2 meter per second. Velocity V naught is given, okay. The vessel is impacting is colliding with jacket platform. The diameter of the legs of the platform is 2 meters, 2 meters. Thickness of the legs is 50 millimeter. Length of the leg 20 meters. So, we will assume a central impact K, the stiffness will be given by 192 EI by L. Now, since P is very less compared to the diameter, that is 50 mm is very less compared to 2000 mm, for a thin walled circular section, I, initial moment of inertia here, is straight away given by pi t dq by 8. Let us compute this for this problem. Pi 50 2000 cube by 8. Can you give me this value? And of course, E is steel taken as 2 10 power 5. I can straight away find the stiffness 192 2 10 power 5 pi into 50 into 2000 cube by 8 divided by L cube, that is 20,000. L is 20 meters. So, if you look at the units of K, let us say Newton per mm square, mm 4 and mm cube, I will ultimately get Newton per mm, okay. So, can you give me what is the value of Newton per mm of K in this example? I get 7.5 10 power 5, that is the K value I get. So, therefore, let us find out the duration of collapse, which is pi by 2 m by K, which becomes pi by 2 3500 tons which will be retained as a mass unit directly, and 7.5 10 power 5, so many seconds. So, this comes to 0.107 seconds, that is the duration of my collision. Now, I want to compare this with the natural period of the jacket leg. So, natural period of the jacket leg is given by an approximate equation which says Tn is 0.28 of ml4EI. So, substitute back and see what is my So, let us compute m, because m of the platform is required. Let us remove this. M, which is m of the leg, it is rho pi dt. So, I can say in tons 7.85, because density of steel is 7850 kg, pi 2.0, that is my diameter, and thickness is 50 by 1000. Yeah, I got so many tons. So, this is going to be 2.47 tons per meter. Is that okay? Is that all right? So, which comes to be 2.47 tons per millimeter. Is that okay? Because I am using the value here like this. And of course, E we know, and of course, L we know, and I for a tubular section pi by 8 d cube T. So, pi by 8 2000 cube into 50, how much is this? 1.57 into 10 power 11 mm4. So, substitute back and find out Tn as 0.28 of 2.47 10 power minus 3 20,000 L power 4, that is in millimeters, 2 10 power 5 and I 1.57 10 power 11, which gives me as 0.031 seconds, because jacket structures are very stiff structures, periods will be very close, okay, very low. Now, comparing the duration of collision T naught with that of Tn, since T naught is very large compared to Tn, quasi static analysis is sufficient. For this impact analysis, okay. So, one can decide like this. So, these two lectures will very briefly talk about the impact analysis fundamentals, which speaks about the necessity of this analysis, the simplified impact modeling, what is a central and what is an eccentric impact caused by a vessel on a platform, how you will compute the most important parameter, which is called the duration of collision, how do you decide whether the impact analysis will remain quasi static or dynamic analysis, with an example. Okay. This will complete the lecture of impact analysis on this. We will move on to the last topic in module 1, which is on tubular joints. So, last topic on module 1, possibly we will complete this either in this lecture or the next lecture. So, we will talk about now tubular joints. Now, there are very important points which we must understand about the tubular connections or the joints in marine structures. Mostly in marine structures, the members are thin walled tubular sections. The moment I say members, I am talking about only the geometric members of the legs, pontoons, etc. Okay, not the deck. Deck cannot be a tubular member, deck has got to be a plate. Generally, these members are subjected to impact forces in addition to combined loading of bending, axial and lateral forces. I should say combined action of. Now, most interesting part is the following: these joints have high reserve strength and capable of redistributing the stresses Therefore, there is a high probability of formation of plastic hinges at these joints. There are three types of analysis which are done for tubular joints, three levels. Three levels of analysis are carried out for tubular joints. One is what we call as a global analysis, where for the given environmental loads that arise from wind, wave, current, etc., local stresses at the joints are determined. That is the first level analysis. The second level analysis is detailed membrane analysis, or you can say shell analysis, to estimate the behavior of the joints under these local stresses. These are the local stresses which are computed. Now, interestingly, at this level, if you see, these local stresses can be high. These stresses can even exceed the yield point stress also, the given material. Therefore, we call them as hotspots. Hotspots are nothing but stress concentration around the most probably welded tubular joints, most probably. Let us quickly see what are the different layout of joints in this lecture, then move on slowly to how we analyze them using different codal provisions, using what we call SCF, that is called stress concentration factors. The third level analysis is a detailed 3D analysis carried out at these hotspots Now, interestingly, the local stress at the tubular joints can result in or can cause fatigue failure. Of the joint. Now, to estimate the behavior of these joints, experimental studies are conducted to arrive at empirical relationships. Because their behavior is very complex in nature. So, people have recommended or conducted and then arrived at certain empirical formulae to handle or to diagnose or to study these joints under hotspots. So, what are these joints? The geometric configuration of these joints, how are they named? We will see that in this lecture. Then in the next successive lecture we will talk about how they are analyzed. We will talk about a T joint, can have P acting here, can have P acting outward also. This is what we call as T joint. This is called as an Y joint, can again have P acting outward, can also have P acting inward. This is called Y joint. Either you can have P acting outward or you can have P acting inward also. This is called X joint. Called K joint. What are the different implications of these kind of joints to estimate their capacity when they are subjected to either inward or outward forces? As you see here, what is the influence of the angle of phi onto the prospective flow direction or the stress direction of the main tube, etc. We will see in the next class. So, we will discuss them, and as I said, the analysis of hot start stresses in these kinds of junctions or joints are complex. People have used empirical relationships and derived what we call stress concentration factors. we will see how they are used for assessing the capacity of these kinds of joints, and that will be the last lecture what we have in the first module. So we have completed almost all the discussions what we wanted to discuss in the first module. The first module talks about introduction to different types of marine structures which we discussed, environmental loads, ultimate design principles, load design principles, plastic analysis and design of sections, beams, frames, etc., upper bound and lower bound theorems, safety factor estimates, then plastic capacity of tubular joints, and members under axial and combined force of bending and torsion, we have discussed that. Then the fundamentals of impact analysis and discussion of capacity estimates on tubular joints. So we will complete this in the next lecture, and first module will be completed. Then subsequently we will discuss the second module where we talk about fluid structure interaction and fluid induced vibrations, FIVs. Okay, thank you.